Okay, hi everyone. How's it going? Um, it's Thursday. It's day 2, and well, day 4 for all of you, but day 2 for me. I'm lucky. So yeah, we are just a couple of quick announcements, reminders. Your first assignment is due Sunday at midnight. Has anyone cloned that assignment yet? Have you gone to the GitHub classrooms? Yeah, you're able to access it. Cloned it okay. That's all going good. Yes, amazing. Okay, quiz 1 opens today at 5 p.m. and then that'll be due Sunday at midnight also. And then the pre-assessment, that's in the week 1 content. Were you able to access the pre-assessment too? Yeah, cool, great, amazing. Pre-assessment, we all know what I'm talking about. If you go to D2L, it's in the week 1. Okay, cool, excellent. So I put a little bit of a poll in Slack just to gauge everyone's, kind of what you want to cover today. So looking at, do we want to talk about basics of cloud, not cloud architecture, basics of computing architecture, intro to Linux, intro to operating systems, that kind of thing. It was definitely everyone wanted to cover computer architecture, which is cool. So we'll definitely do that. We're going to definitely do a intro to Linux and kind of operating systems, but just at the level that I think is important so that when we get to containers, there's a little bit more intuition for how containers are working and how they provide isolation and all of those things. And then we're going to do if we have time, which I think we will, I'm going to do my best. We're going to talk about open source software just really in brief, but there's so many people here who are have a lot of depth in open source. And so I'm hoping that's more of a discussion focused on open source and cloud and why cloud computing and open source go hand in hand. What are the pros and cons? Okay, so let's get into it. So what is computing? Basically, computing is just the hardware, the applications, and the development of computer software, right? It's that's what we're talking about when we mean computing. So that can comprise a lot of different things, a lot of different kinds of resources, we call them. But basically, we can define computing as any goal-oriented activity that requires, benefits from, or creates computers, right? So that can be your software, that can be your hardware, that can be your networking. All of that comprises computing. So when we say cloud computing, it's just all of that, but in the cloud. So compute resources are going to be these measurable quantities of compute power that you can request, you can allocate, and you can consume for computing activities. So does anyone have an idea of what a compute resource might be? RAM, yeah. Storage, absolutely. GPUs, yes. Yeah. Yeah, graphics cards, GPUs, yeah. Anyone else? CPU as well. Yeah, don't forget about those. I know it's 2024, but CPUs still matter. Yeah, great. Those are all good examples. So we covered, everything except for network. I think no one said network, but yeah, we're talking about processing power, memory, network, storage, anything else, GPU that you can think of that's required for computational success of any program. We can also in more enterprise IT kind of on-prem data server room world. We also talk about input and output devices as part of computing, right? Like peripherals. But since we're doing cloud computing, we don't have any peripherals. It's all just, unless you're doing IoT and you're using Cloud Connect IoT. But for the most part in this class, no peripherals. All of your input output is going to either be disk read and write, or network bandwidth transmissions. So yeah, there's nothing to plug in. Okay, so let's start with the CPU. We're all pretty familiar with CPUs in general, but yeah, the CPU is just going to be in charge of all computation on your computer, obviously. The first mass-produced CPU was the Intel 4004 in the late 60s, which is wild to think about. That was a long time ago. And that had a 4-bit architecture, which is so cute. Oh my God. So today the common architecture is 64-bit architecture. So before I get into that, can anyone tell me what we mean by 64-bit architecture? Yeah.
Calculations are 64 bits of precision, or
I'm thinking more about the from the perspective of what you feed to the CPU, like what you feed to the processor, as opposed to the bits of computation. I guess that fits. Yeah. Did you have?
Yeah, so you feed 64 bits of information at a time rather than 4, so everything's a lot faster.
Yeah. It's 64 bits of instruction that gets passed to the processor. Is that what you said? And I
No.
missed. Oh, okay. All right. Yeah. Because as far as like, because you mentioned memory, right? Or like the amount that it can process, it could actually have a lot more than just 64 bits that it can work with, right? But what's passed to the processor itself is 64 bits of information. Or 32 bits. That's still really common today. And we're going to get into that a little bit. The history of 32-bit versus 64-bit doesn't make any sense. And it's really just a history of like naming conventions and jargon and stuff. Anyway, so how do we read, how do we get 64 bits of stuff to our CPU? We've written a program and then that gets assembled. And that program, when it's assembled, the language that it's in is called assembly. And assembly is really just, it's supposed to be more helpful syntax for reading and writing machine code. It's supposed to be easier for humans to understand. Not this human. I got nothing when it comes to assembly, but people do. And if you're like a reverse engineer, if that's your job, that's your gig, that's awesome. You're working in assembly all the time. So assembly then gets compiled into machine code. And machine code it's generally in hexadecimal notation. And that's going to be a series of binary instructions kind of in a row. And then the machine code gets translated into the actual binary. And binary is what's actually passed to the CPU, right? So you've got assembly, machine code, binary, and then the CPU reads that binary instruction. So it's not needed at all for this class. I'm never going to ask you like the order of binary instructions or anything like that. But just, there's certain bits that are allocated for certain things, right? So there's something called an opcode. And opcodes, anyone? No. Okay, so opcodes basically are just going to be these little bits that signify to the CPU what operation it's going to do. So it needs to have like some place in memory that it's going to go jump to or do the thing, and it needs to have an opcode. I will never test you on like the order of the instruction bits. I promise. It's just, I don't know. I think it's fun to know. Okay, so memory. RAM is our computer's main memory bank. And memory really is just storage. It's really just like where we're putting a bunch of stuff that the CPU needs to be able to read and load so that it can run program. It's just this like large multi-purpose space, and it's going to store all of that data for your program. It includes the program itself, as well as like code at the core of the operating system, right? So that has to be like in memory for your CPU to be able to do things with it. So we'll talk about what the OS kind of abstracts away and, and how that works so that it can give you access to the underlying hardware from your program. Any questions there so far? Okay, so the CPU is going to read this machine code directly from RAM, but that code can't be run unless it's loaded into RAM, right? So it has to be there, it has to exist. And so how is your CPU going to access that? Basically, there's something called an instruction pointer, or sometimes it's called, the instruction pointer and the program counter work together. And that's going to point to the location in RAM where it's going to fetch the next instruction. So basically, we have here we have a program counter, and that's just going to kind of keep track of which program is running. We have our instruction register, which is going to hold all the locations of where that instruction actually lives, and that's going to keep looping through. So this is called a fetch execute cycle. So when you fetch, you're going to read the instructions from memory at the place where the current instruction pointer is telling you to go read it from. And then you're going to execute, you're going to run that instruction and then move to the next instruction pointer. And again, those instructions can be, well, we'll talk about instruction sets because that's part of computer architecture also, right? You can have complex instruction sets, which means that there's a bunch of stuff you can do. And there's like so many different calls you can have and different instructions. And then you can also have a restricted instruction set. And those kind of define sort of two categories of computer architectures. And we'll get into the like examples of those, and that terminology is going to become real familiar real fast. So, okay, the instruction pointer is going to just keep moving forward. It's going to execute your machine code in the order in which it's been stored in memory. And the instructions are going to tell the pointer to jump somewhere else, or they can tell it to jump somewhere else, depending on certain conditions, right? So this is where you can do conditional logic. You can do like flow control. Your instruction pointer can go, okay, well, if we have if this, then that, right? How is it going to run that? We have instruction pointers that can jump to other places. And that makes your code reusable also, which is very nice. So all of your instruction pointers are going to be stored in this thing called a register. And those registers are just like, all it is like a specific bucket of storage for instructions. It's really, really, really fast for your CPU to read those and to write to them. So each CPU architecture has a set of registers, and that's used for everything. It can store temporary values during computation, right? Your variables, and it can also configure the processor. Your register is a super critical, important piece of your computing architecture. Am I going a little too fast? Should I slow down? When I watched that first recording, I was like, dang. All right. Yeah, but any questions for now? Okay, let's keep going. All right, so these are these different CPU architectures, right? And they're really just defined by the instruction set, right? So that the kinds of things that are available for you to call like on that underlying hardware. So this is like the families of stuff. We're going to get into this. So we have the complex instruction set, and we have the reduced instruction set. And so under these, we have these umbrellas of different kinds of architectures, right? So we have Intel and we have AMD under the complex, and we have ARM and then RISC-V, which is a newer one under the reduced instruction set. So Intel, has anyone heard of like Intel x86 or Intel x64? Yeah, so those names are more familiar. This is like just how they're different, how they're organized. The bummer is that like x86, right? So that x86 is how many bits of instruction, or how many bits can the CPU read from the instruction in x86? Anyone know? It's not 86, unfortunately. It's 32. So that actually has like, I don't know, it's real messy. And again, it has like lots of naming convention background and history. But yeah, 64 is like the more modern one. And AMD kind of pioneered x64. Originally, Intel came out with the 32-bit, which was called x86. And then AMD was like, hey, we can do that too. We're going to do it with 64 bits. Then Intel's like, hey, good idea. Why didn't we think of that? And so then they did x64 also, but they left the 32-bit one called x86, even though x86 32-bit architecture can actually still read more stuff. Yes.
So is x86 just like a brand then? Or does it?
Oh, that's a good question. I guess you could think of it like a brand. It's like the yeah, it's really just like a name.
Okay.
Yeah.
Isn't it? So
So old I want to say in like, yeah, go ahead.
because the microprocessor that they used for it was called the 8086.
Yeah, something like that, right? The 8086, yeah. So yeah, and then it just kind of persisted. And then we kind of adopted this like more colloquial understanding of what x86 was, and like the colloquial understanding was that it's 32-bit register as opposed to, yeah. Anyway, yeah, so then ARM architectures are, the common ones are ARM64, and then Apple Silicon is based off of ARM. And then we have RISC-V, which is, oh, that looks like Apple Silicon is under RISC-V. It's not. Apple is ARM. I hope that's, yeah, my line's not that clear. Okay, so let's talk about the complex instruction set computer. So like I said, this is a rich instruction set. It's going to be compatible with a lot of different software, lots and lots of different software. And it's really what's used in like historically in most, personal computers and most personal laptops. Now, ARM has a larger share of that because of Apple Silicon and other reasons. But yeah, but your Intel chipsets are still everywhere. And Intel like x86 is like compatible with Windows, Linux, Mac OS in the old days, and your older Macs. And yeah, they're great. They're really, really powerful, lots of computation power. The one drawback for them is that, there's a lot of heat generation from those chipsets. And so that makes it a little less ideal for, if you have a lot of computers in a small place, right? Where won't we have a lot of computers in a small place? A data center. Yeah, and also, there's so much that it can do. In a lot of like cases like IoT, you don't really need that whole instruction set. You don't need it to be able to do all kinds of fancy stuff in memory because the little program you wrote for your Arduino is like this big, it doesn't, whatever. So, and actually in those cases, having a limited instruction set actually helps that entire ecosystem because you build off of each other's work a little bit more easily. So the rich instruction set has like a higher code density just because you can do a lot more with it. And so it has also a lot of high performance in parallel processing. So it's really good for gaming. It's really good for video editing. We're going to talk a lot about like parallelism and how we make things run in parallel using time slicing. Okay, so the RISC instruction set, this is the reduced instruction set computer. And so it's a lot more simple compared to the CISC instruction set. And it's going to be faster execution, less power consumption. It's real fast. If anyone went from the older MacBooks to the newer MacBooks, you start to see the benefit of these ARM processors and just like how fast it is, it's kind of extraordinary. So it's high performance, it's memory efficient, and that's going to be those qualities let it be really appropriate for servers, for supercomputers, and embedded systems. So what's an example of an embedded system? What was that again?
A home automation system. Any IoT
Yeah.
device?
Yeah, any home automation. Yeah, absolutely. Any IoT. Yeah, anyone else? What about industrial control systems? Yeah. So those are, I mean, they can also, they'll use ARM to also use some of their own specialized architectures as well. The backup mirror in your car, any of that, that's probably using ARM. So ARM stands for the Advanced RISC Machine. And so that's building on top of RISC. And so it's kind of optimized for the highest performance with like the lowest amount of power. And so, yeah, it makes it, there's a bunch of different manufacturers have made kind of their own version of ARM processors. So like Samsung makes theirs, Qualcomm has them, Apple obviously. And yeah, they all produce these chipsets that are for ARM, these chipsets that are for ARM. So yeah, smartphones, tablets, mobile devices, IoT, all of that. Okay, so when we go, like, why do we care about all this for cloud computing? It's not just like, oh, here's our cloud databases or cloud data centers. It's actually because when we go to choose a virtual machine, when we go to spin up a virtual machine in the cloud, we get a choice of processor. Well, a choice of a virtualized processor, but yeah, you kind of get the underlying benefits of that architecture. So those are going to show up in a lot of different ways, right? So if you go to GCP, for example, Google Cloud Platform, and you go to spin up a machine there, one of the first choices you get is going to be the architecture. And so you can choose Intel. You can choose, there's a new one called Intel AMX that's really big on Google Cloud right now. It's just like a newer, it's a newer instruction set. You can choose AMD, you can choose ARM. So you have all those options when you're spinning up a VM. We're going to give you a lot of guidance on like which VMs to choose. Because once you start putting together all the options, yeah, the search space gets a little unmanageable. And that's just the CPU architecture, let alone the actual image, the operating system you can use, let alone all the things. So yeah, it's just good to be aware of all these different options. Yeah, okay, so let me pause there. That was kind of like the overview of computer architectures. We're not talking a lot about storage and networking just yet because I feel like, well, first, like storage, I think is just a little bit more tangible and familiar for people because we interact with it more every day. Kind of same with networking a little bit. And we're doing such a deep dive on networking in 3 weeks. So you'll get a lot of that. But yeah, so as far as like computer architecture, this is what I brought. Does anyone have questions? Would you like to go more in depth about something? I can prepare some readings or some videos or whatever you'd like. Or you could give me feedback after class too. but I just wanted to like lay the foundations of all that and where we're going with this. Okay, so operating systems. I mean, I can pause. Who wants to give it a shot? What does your operating system do? What is your operating system?
And it's provides an interface to talk to the CPU or any of the machine.
Yeah, perfect. That's a perfect definition. It's software that provides an interface between you and your machine. Excellent definition. Yeah. So it's going to, yep. You could do you want, yeah, we should just switch places. Yeah, it's just going to take care of all the basic stuff. So you don't have to. If you had to do all of that, if you had to really like handle all of your memory management on your own every time you wrote a program, that would not be ideal. It's just going to abstract away all the different hardware components through this application programming interface or an API. So you've definitely worked with APIs before, even if like you're not if it doesn't feel like you're super confident with them, that's okay. You've worked with APIs in like 531, for example, when you're writing your SQL program and you're running that SQL on your Oracle server, right? Whatever it is. Underneath that, there's like APIs that are being called and like it has like a specific syntax so that you can actually run those queries. Yeah, so your operating system is going to abstract away your memory management. It's going to do interrupt handling for you. It's going to talk with your I/O devices for you. So you can do things like plug in your phone to your computer. It just handles all the things. It's going to manage files for you, which is great. And then all of your network stack. So you don't need to be like, okay, well, let me set up my L2. Like we will get into IP tables a little bit, but that is interfacing with your operating system and not with lower level hardware, right? Okay, so we're going to talk about processes because processes are really important, well, for everything that we do in computing, but processes get really interesting when we get into containers. So your program, any program that you write, that you're running, it's on its own, it's going to be this passive collection of instructions that are stored on as a file on your disk, right? In order for that program to do anything, a process has to be instantiated, and that process is the execution of those instructions. So you want to launch Chrome or PowerPoint or whatever it is, there's going to be a process that spawns, and it's going to execute the instructions that correspond to that program, right? And yeah, you can have a lot of processes with the same program. So I just took a screenshot of like, this is me and like Chrome, and like you could just keep scrolling. Like I don't know, I do have a bajillion tabs open, but even still, if I had like one tab open, it would be, you can just keep scrolling. So Chrome has a bunch of processes open. There's going to be minimally one per tab. There's Chrome helpers, all these things. So these are all processes that are there just so that I can, rabbit hole down the internet. So yeah, you can check it out on using Activity Monitor on your Mac, or on Windows, it's Task Manager. Thank you. Yeah, and you can just inspect all the processes that are running, how much CPU they're using, what the CPU time is. We'll talk about that in just a little bit. How many threads are going? Threads are up next. Yes.
About Chrome, like especially is so like it takes up so much computing power just because it has so many processes and instructions behind it.
That's a really good question. Is that why Chrome? I mean, yes, like ostensibly, that is the unit behind which Chrome is taking up compute power. As far as why it spawns this many processes, like I don't really know. Yeah. Is anyone like a Chromium developer? Did anyone like get into that? Because then you could tell us. I never did, so maybe that's my next project. Give me a year, I'll come back and answer that question. Yeah, okay, so multitasking. Okay, so here's the thing about CPUs is that they just run one thing at a time. It's going to run one little process at a time. So how can I have all these things open at the same time? Like, how can I be running PowerPoint and also like OBS Studio? And then also, I'm not live streaming, by the way, it's just for recording. And then also, all the other things. We use multitasking. And so multitasking is how we allow multiple processes to share processors and share other system resources. So what the CPU is going to do is help you switch between these tasks. And those are all being executed like basically without having to wait for each task to finish. And that's called preemption. So we talk about preemptive processors. And so, yeah, we can have Word. Let's say Word has one process going, email has one process going, web browser is one process, and antivirus is one process in a perfect world. And then we have our operating system. The operating system is going to help us do our multitasking so that those tasks don't have to finish before the next one starts, right? And we just know this intuitively from having used computers. Yeah, depending on the operating system and the implementation, switching between those processes could be performed like either when a task like initiates and you can wait for a completion of input-output operations. That's less common, right? Imagine if everything stopped while you uploaded a file, to like Google Drive. That'd be insane. A task can voluntarily yield the CPU. It can say like, okay, well, I don't need this for now. Come back to me though. It can do it on hardware interrupts, which you can also interact with your OS. If you've ever done Control-C, try to get out of, kill a running program. Or you could do it. I can switch when the OS scheduler decides that a process has expired its fair share of CPU time. So CPU time is the really fun thing about all of this because CPU time is how we actually do multitasking. And that's done through something called time slicing. So time slicing is basically it's like timeshare, program. It's not a pyramid scheme. It's CPU architecture. You guys are too young to know about timeshares. That's fine. Okay. So time sharing is just going to help like interleave the execution of these processes and then actually the underlying threads, but we'll talk about threads in just a little bit. It can even interleave independent kernel tasks, and we'll discuss kernels also. So some processes are going to get higher priority. So this process is running and we're doing like time sharing on the CPU, like this one starts, it gets this much time, the next process goes, gets that much time, right? But then there's some processes that are going to get higher priority. So if you've ever heard of like, background processes or like, background services, those are going to get some lower priority. Arguably, it doesn't always happen that way. If your AV has ever slowed your computer to a crawl, it's getting a little bit more CPU time than it probably should. So things that get higher priority are going to be like anything that you as a user are doing. Users just are immediately assigned computing resources when you press a key, when you move a mouse, that program's going to get more priority. And then, basically the whole thing is that this context switching happens so quickly that it just gives the illusion that things are running at the same time. That makes sense? Pretty cool. All right, and that's called concurrency, right? So when we talk about concurrency, we're talking about we're faking it. We got one process or one processor, and it's just going really, really, really fast between all these different processes. So it looks like it's running at the same time. Yes, please.
So is this parallel computing?
Is this?
What concurrency does this parallel computing, or parallel computing is entirely different?
Parallel computing? Oh, yeah. Parallel computing is a little bit different, but we'll talk about that in just a second. It's related to parallel computing, but that comes along with like threads. So we're talking in this case about processes. But I think we're getting into threads in like 2 slides. Yeah, but yeah, great question. Okay, so the operating system's job is to keep all these processes separate, and it's going to allocate resources that those processes need. It's going to give it the memory, the compute, the network, the bandwidth, all this stuff, and so that they are less likely to interfere with each other. When processes interfere with each other, bad things happen like deadlock or like thrashing, and then you get a stuck machine. The OS, if you want processes to talk to each other, the OS is going to handle that as well. And that can be done through like memory, that can be done through disk, can be done through all kinds of things. So in general, we want memory to be distinct. No one gets to read my memory, right? This is mine. No one gets it. You all get yours. We're all processes. This should all be like our personal space. When you start to be able to read memory from other processes or from other threads, that is not good. We do a lot of things to prevent that from happening. It's kind of the history of computing in the last, 50 years. How do we keep all these things separate? Okay, so we've talked a lot about processes, so now let's talk about threads. Processes are just like the instantiation of your program, so that can execute that, so your CPU can execute that program. Your processes are going to be executed by one or more threads. So your process can have multiple threads too. And then the thread is really just it's the smallest unit, the smallest sequence of instructions that can be managed independently by an OS scheduler. So schedulers they're the ones that handle the time slicing, they handle the interleaving of processes. And multiple threads of a given process can be executed concurrently. So that's through these like multi-threading capabilities. And so because they can be executed concurrently and they can be multi-threaded, they can share resources. They can share memory, but processes are not going to share memory, but your threads can share memory. So has anyone ever done some like multi-threading in Python? Or yeah. Yeah, so you can set up a variable that like multiple threads can read if it's in global, right? If it's a global variable in your program. Yeah, and you can basically have threads that are all executing the same thing, or something in a loop, for example, is a common use case. Has anyone ever done any like web scraping in Python? Yeah, a little bit of web scraping. Or yeah, maybe you're trying to. Yeah, let's use the web scraping example. It's top of mind these days. So say I have to scrape 1,000 websites, or let me rephrase that, 1,000 web pages from the same web app. And I know that that's going to take a certain amount of time per page. What I can do is I can set up multiple threads to kind of chunk out I'm going to give my program a list of these 1,000 pages that I wanted to scrape. And then I can use in the Python standard, is it standard library or is it in more utils? Doesn't matter. There's like, you can create chunks of that list, right? And then once you have chunks of that, you can say, hey, this thread's going to go take that chunk, this thread's going to take this chunk, and then they're going to go out and scrape those sites independently. So it's still just one process, but say you use 4 threads, it's going to do it 4 times as quickly, right? Which is cool. Multi-threading in Python is pretty straightforward. That doesn't mean you're not going to get rate limited, or that like the web app owner isn't going to get mad at you, but that's an orthogonal topic. Yeah, so yeah, the threads of a process share the executable code, and it can share values of variables. So any variable that's dynamically assigned or any called non-thread local global variables. So it's like a global variable that's set at the top of your program, right under your import statements, right? Okay, any questions about threads? We have a program. It's going to launch a process. That process has lots of threads, or one or more processes, and those processes will have threads. Okay, so we talk about services a lot too, right? So you ever look at your Windows, from our Windows people, like your startup services? Like, your machine starts running real slow and you're like, what is it doing? And then it's like Norton has like 18 startup services. You're like, what? Does anyone relate to that? Yeah, it's just Microsoft Teams, yes. Yeah, so a service is going to be like a coherent and related, a set of coherent and related functions that can be reused and integrated into bigger and more complex applications. So the service is an abstraction that's going to encompass a few different like implementations, depending on like what you're talking about. So it can include different protocols, different technologies, things like that. So the service is going to be software that's going to perform some automated task. If you ever set up like a cron job, something that you want to run like every day, that kind of runs as like a part of a service, right? It can respond to hardware events. So you have there's going to be a service that like when you plug in well, no one does that anymore, but like if you plug in your earphones, there's a service, some like audio device driver service that's going to handle making sure that that's going to function correctly. And it's also going to listen for data requests from other software. So services just kind of, there's these like handy little, oh, sorry, that's, yeah, that's me. Sorry about that. Yeah, I don't know what I'm doing with this. I like just picked this up. Oh, connection lost. Sorry, 1 second. Doesn't matter. I haven't written on the board at all anyway. So, okay. I'll just turn it on if I do write on the board. Okay. So yeah, we have a lot of different services that are going to accomplish different functions or different tasks so that like we can just have a happy, friendly compute world. You can also set up programs of your own to run as services, right? So sometimes we'll set up databases to run as a service on like whatever machine you have it on. Yeah, so it does lots of fun things. They'll respond to user keyboard shortcuts. If you set up some like automation through like your through what is it? What is the Mac automation tooling? I don't do it because I just use Python for everything. But yeah, if you set up some like automation, like cron jobs or whatever it is, or like I move this file here and I want it to be automatically uploaded. Okay, there we go. How about Google Drive like sync, right? So that's a service under the hood. So that's going to look for responses in like movement and new files added to this location. And there's a service underlying there. It's going to listen for that. Okay, so let's talk about operating system kernels. Yeah, anyone ever get an error message that says there's a kernel panic? Yeah, don't we love a kernel panic? Okay, so a kernel is, we don't love kernel panics. I'm sorry, that was yeah. It's not a good thing. Okay, the kernel is the actual core of the operating system. When you boot up your computer, basically what happens is your instruction pointer starts going, but the first thing your instruction pointer goes to is the kernel. It's the first program that gets run. It's going to contain all the bits and pieces to boot your operating system, like first and foremost. It has near full access to your computer's memory, full access to peripherals, access to resources, and it's going to help facilitate running software that's installed on your computer. So your kernel is going to be here in your OS. And then all the programs that you install, so maybe it is that Google Drive like sync, right? That is going to be a user land program. So we have kernel space and we have user space, sometimes called kernel mode or user mode. And those distinctions are super important. And we're going to talk a lot about that in containers. And kernels are, they just have so much more control. If your user program really gets access into kernel space, bad things happen because your kernel can, it's the bit that ties your operating system together. So it can, interrupt for example, your OS scheduler. And that would not be good because that can crash absolutely everything. Kernel panics are so disruptive because it just means that literally everything's ground to a halt. If your kernel's not operating, nothing is. Yes.
Doing some operations that kernel crash.
Yeah. Not great. They put out the full report of the CrowdStrike, the full root cause analysis. It's actually a pretty interesting read. I can put in the course details if you'd like, or for reading for next week, to get a sense of how gnarly that was. So when we talk about Linux, like Linux itself, what we talk about when we say Linux is just a kernel. The kernel in Mac OS is called XNU, so X is not Unix. Linux, origins were Unix, and the Mac OS kernel is XNU. The modern Windows kernel is called NT, right? So if you see any like NT things, that's the Windows kernel. Okay, so we talked a little bit about kernel mode and user mode. In kernel mode, the CPU can execute any supported instructions and access any memory. That's a lot of power. That's a lot that it can do. So the drivers all run in kernel mode because it needs to be able to do stuff that like user land programs don't need to do. And then in user mode, there's only like a subset of instructions that are allowed. So IO and memory access is limited. And then a lot of the CPU settings are like super locked down in user mode. And most of your applications are going to run in user mode. This is just like kind of nerdy. I'll never test you on this, but there's different privilege levels or rings, we call them. So the current privilege level or CPL, that's read from one of our registers called a code segment. So remember, we have these registers with these really specific storage units that include instructions. The CPL is going to be in 2 bits of this CS register. So kernel mode is bits the kernel mode for CPL, sorry. In CPL, the kernel mode bits are going to be 0, 0, and then and that's called ring 0. And then ring 3 is going to be user mode, and that's going to be bits 1, 1. So you're like, wait, there's room for more. So what happens with like ring 2, ring 1, ring 2, like what happened to those? Those are really just used for drivers. And they were sometimes used by older operating systems, but I don't remember them. I don't know which operating systems. Allegedly, they're used by older operating systems. I haven't seen it in the wild, but you know, but 1 and 2 are going to be used like more for drivers, like peripherals. So if you hear about rings in Linux, or if you hear about rings in container world, then that's what it's talking about. Your kernel ring, your user ring, 0 or 3. Okay. Syscalls. So remember when we talked about operating systems have an API, you don't need to read all of this. You can read the slides. I uploaded them in D2L. Yeah, I know it's a lot of text on one screen, but basically the reason that programs can run in user mode, like it's all locked down, right? So like how would your program even like, and maybe it needs to print something, right? Like how is it gonna be able to send that signal to the underlying kernel so that that can send it to the device driver, so that that can send it to your computer. And it's not just the printer device driver, it's also the network device driver, right? So that's a lot of interaction with like underlying hardware. So how is your user land program going to do that? It's going to do that through syscalls. And syscalls are what the operating system allows you access to via APIs. So there's like specific syscalls, open, read, exit, those kinds of things. And yeah, these abstractions over the system calls are basically going to ask the operating system for help. So your user land program is going to be like, I got to do a thing. So it's going to ask the operating system for help through this API. Did you have a, oh, sorry, I thought I saw it. Yeah. Yeah, you can read the rest of this. Again, this isn't going to be tested. I just want to make sure everyone's on like same page for like, you know, kind of how all this works, especially when we get into virtualization, because there's another layer of abstraction, right? So how do all these things stay separate? How does it all talk to the underlying hardware? How does virtualization like truly work? So that's why we're going over all of this. So yeah, it's really just getting the gist of it. I don't care if you know details about this, just like how things kind of interact. Okay, wrapper APIs, I think I already covered that. So yeah, this is way more detailed than I need. So like DLL files on Windows, right? Those are going to be library functions that wrap like the assembly instructions for libc. So that's going to be like, you're going to see a lot of DLL files on like Windows. So it's going to be like part of the, they're called dynamic linking libraries, right? So that's going to be part of how your program is going to interact with your operating system through dynamic linking library files. It's a whole thing. So yeah, there's different architectures or the different ways of doing this for both RISC-C and for CISC. So those are going to have different instructions available for your system calls. Okay. So back to OS schedulers, they're using these timer chips to trigger these hardware interrupts for your multitasking. Why did I have this slide here? I'm sorry, this is out of order. My apologies. Oh no, because I'm going time slice calculation. Okay. All right, cool. So yeah, your program needs to talk to your operating system. One of the ways that it does that is through these hardware interrupts. Those are abstracted away and like available to you through your operating system, like APIs, through syscalls. And some of what those syscalls are going to be doing is doing these hardware interrupts. And so your OS scheduler is going to use these timer chips to trigger hardware interrupts for your multitasking. So your programs can do multiple things at the same time. So time slice calculation. Basically, yeah, I think actually I already covered this. Is there anything new? Oh, I guess it's just a little bit more detail. Sorry, I moved things around a lot based off of that Slack poll, and that was maybe a mistake. So there's two primary ways of doing time slice calculation. The first is going to be round robin. So that's just like every process is going to get the same time slice. 10 milliseconds, right? Which is going to keep going and then start at the beginning again. The second one is going to be, there's some target latency. And so there's going to be, you know, this ideal longest time for a process to respond. So the time slice is going to be, you know, you take your latency, your ideal latency, you divide that by the number of processes, and then that's the time slice that's available. So if your latency target is 15 milliseconds and you have 10 processes, and they're each going to get 1.5 milliseconds to run. Yeah, so that's the primary way that Linux does time slice calculation. And it is something called a completely fair scheduling something. What is it? Sorry, completely fair scheduler. All right, there we go. So yeah, every time the OS goes to preempt a process, it's going to load the new program's saved execution content, including the memory environment. And it's also going to prevent other programs from accessing each other's memory, right? So this time slice calculation is super important. And yeah, all modern kernels are really these like preemptive kernels where it's going to kind of prepare that next memory bit. And for my security people, preemptive execution, any familiar massive security events pop to mind? What'd you say? Oh, Spectre. Yeah, Spectre is one of them. Yeah. And Meltdown. Yeah, this preemptive. Yeah, I'll post some information about it. But yeah, because of this speculative execution, there's a lot of gnarly stuff that can happen. I think we're in a better shape now. But 10 years ago, when we're like, wait, preemptive execution can be problematic? That's terrible. Everyone was shocked. It was shocked Pikachu like across the entire world. Okay, so moving on. Now that we have gotten through like our operating system, we've talked a lot about computer architecture, how your operating system kind of works with your computer architecture, things like that. Let's talk about Linux. So everyone's heard of Linux, right? Well, yeah. Has anyone like played around with Linux much? A little bit here and there? Any distros that you've installed locally or? Sure, yeah. Yeah, nice. Yeah, cool. Oh, Kali, yeah. Mhm. We all have a friend who runs originally. Um, yeah, anyone else or anyone have like a little bit of familiarity, like maybe you've or like for Mac users, you're a little bit more familiar with some of the like Linux, like the Unix like commands that you run. Anyway, so we're going to do a lot of Linux this semester, so I figured probably a good idea to kind of do a high-level overview, think about all these different distros and like why are they all different? Why can't we just have one Linux? Like we have Windows 10, so Linux is the most widely used operating system in the world, and probably just like the most widely used software in the world. It's free and open source, which means that you can install it anywhere that you'd like to. Android is based off of Linux. I forget which distro. If someone has that top of mind, let me know. But yeah, basically every Android device is under the hood running Linux. It's gotten really, really big in cloud computing, and we'll talk about that at the end of the lecture. But yeah, the Linux kernel. So just remember that kernel is just really that core set of instructions that that defines like your interactions with like your peripherals and all these things and all the underlying hardware. The Linux kernel is that set of syscalls and device drivers that are provided as part of the Linux OS, right? So the Linux kernel is kind of like it's like a commonality between all of these different distros. Then the distributions, the Linux distros, those are these like bundling of like the kernel and any related components. So that could be like your package management tooling, your file system layout, the shell that you want to use, and that's all kind of pre-selected for you. So there's some distros that have a lot of like userland programs pre-installed, like Kali, for example, just comes prepared with everything you ever need to be a pen tester. Except for Ghidra. And then, but pen testers don't use Ghidra, do they? Then you have like some really like pared down distros like Arch Linux, right? And those are really customizable. A lot of people, will use Arch Linux because they want it to do a very specific thing, very specific way, very picky about how things run. So here's the thing about Linux. Do we have to? We really do. I'm so sorry if this causes a lot of deep dread. We're going to get through it together. I promise no one's going to get left behind. But why do we have to? There's broad support for Linux from basically everything. A wide variety of software is available. And I know like a lot of like end user software, right? It'll say like download for Mac, download for Windows, and those are your options. There's such a huge world of software outside of that. And all of the software kind of outside of like productivity stuff or like entertainment apps or whatever, all is kind of like Linux first. And so there's a huge amount of support for Linux. It's really customizable, it's really flexible. And then it's really compatible with modern DevOps practices. And we'll talk a lot about that when we talk about infrastructure as code and like configuration, but it just lends itself really well to being able to have like, carbon copies of itself kind of deployed in a lot of different ways. It's also open source. So can I get a quick definition of open source software? Yeah, it's free. It's available to anyone who wants to use and download it. You can modify it. You can contribute back to it. You can make it better. You can share it with people. You can package it up in your own thing, even if you're going to sell that thing. Well, depending on the license. Yeah, but you can like reuse it, repurpose it, whatever you want to do. So Linux is open source. It's free to use for everyone. You can modify it. And that helps you kind of avoid vendor lock-in. So does anyone know what I mean when I say vendor lock-in? How about in the back? Have you heard of vendor lock-in? Does that ring a bell? It's basically like if you ever go to like Costco and then you have your Costco membership and then you're stuck with that membership because you signed up for like 3 years or whatever because it was like cheaper when you were graduating. I don't know. And then you're stuck with that. Like that's your option. I guess like vendor lock-in was a lot more common, is more common in like the Windows ecosystem world, right? Where you pay for seats, you pay for licenses, in like enterprise IT, you get sucked into the Windows world and it doesn't always play that well with other ecosystems. And so you keep getting more Windows stuff and then you have to start using Azure for things and you have to, right? And so you get stuck into this world of one vendor. Using Linux, you can kind of avoid that a bit, right? You can run Linux kind of wherever you want to. And it's gonna work. So it's also just, there's overall ubiquity in server computing on Linux. Yeah, even in Microsoft shops, even in Windows shops, there's going to be some server somewhere that's Linux, guarantee you. And that's because it's really easy to customize and configure, and you can configure any task that you want to, kind of in the way that you want to run it. There's, well, people say enhanced security, kind of. The Linux kind of makes security a little bit more discoverable, I would say, and we'll talk a lot more about that. It's really stable. So you have your Linux kernel, and like you don't really get patches that break your entire, that like brick your machine, right? If anyone's ever done like an ill-fated in-place OS upgrade, Mac or Windows, whatever it is, and it's just you're kind of done. I guess there's something weird going on, but like Linux is super stable. And so, and also has really long-term support. So you can have an older version of Linux running, and there's support for 5 years, which is really nice. So you don't have to get bothered, or like things are not going to be, you're not going to get annoying emails as a sysadmin. It's like, hi, your AV software is not going to run anymore unless you update all of your things in the next 2 months. And you're like, oh, I oversee 300 users. What am I going to do? Not like that's from experience, but you have just like long-term support. There's fewer surprises. So, okay, so in Linux, processes, right? Going back to processes. Recall that a process is just a program that's in memory. It's going to have all the necessary resources available to run, has CPU, has memory, has all those things, right? Linux is going to identify a process using a process ID or a PID. PID. So PID1 is a special process ID, and that's going to be reserved for the root of the user space process tree. So we talked about how a program can have multiple processes. PID1 is going to be like the kind of the heart. It has top priority over everything. And the really weird thing about Linux and about computing in general is that if this is at the root of your user space, it might be a surprise that multiple processes can have PID1. That seems like really weird, right? Like how could multiple processes have the exact same top priority, right? And the way that we do that is through something called namespaces. And we're going to use namespaces in so many different contexts. We'll have namespaces, not just like, for a single machine. We have namespaces for containers. We have namespaces for Kubernetes. We have namespaces kind of everywhere. So this idea of namespaces, where basically like you have a little cluster of things that's called a certain thing, and that's how you know that it's its own thing, distinct from others. Turns out that happens a lot. It's everywhere. So we'll get a lot of depth into namespaces. So so if you're running Docker, for example, then you can have multiple containers that are running, and they can each have their own PID1. And then the underlying like virtualization software is going to take care of keeping track of all those PID1s and how they're going to interact with your hardware and your hypervisor. That is also going to help create this. These processes running in parallel are going to have restricted visibility into resources. I have a better picture on this next slide, so we'll just go there. So we have process 1. It's going to have all of its threads. We have our CPU scheduler, right? So that's the one that's going to keep iterating through all of our processes. And then we have these things called C groups. So C groups are going to be how we get isolation, how we really separate out memory from all of these different things. So you have C group 1, C group 2, C group 3, C group 4, and the C group's job is to provide isolation so that you can't read memory from other places unless you explicitly allow it, right? So in that case, you would have, your threads running. If you have like your Python web scraper, right, you have multiple threads running in the same C group. But yeah, that's how you get this this isolation. So you can start to see how between, having namespaces, kind of creating its own like priority processes, right? Its own like process tree. And process isolation and a CPU scheduler, it starts to look like each one of these, each process or each program is kind of running its own little computer, right? It's like, it kind of has everything it needs. It looks like it's really autonomous. It's kind of its own thing. Is that kind of starting to make sense? Does that feel intuitive at this point, or no, not so much? Not so much, maybe. Yes.
So it's like a sequence, so it's a grouping of threads that are delegated to specific process.
Yeah, it's well, the C group is really looking at process isolation, which includes like memory isolation, right?
So it's like a whole memory.
Yeah, the whole thing. So, and it's you can think of it as like a permission group almost. Yeah, so it's like a resource group with specific permissions on it, around it. And then that's only going to be available to the process or the thread that needs access to it. Yeah. So C groups are like a key security control. This is how we can have multiple programs running at the same time that don't have access to each other's memory. C groups are foundational multi-process security there. Yeah.
What does C stand for?
Wait, that is a really good question. I don't think I know. I don't know. We just call them C groups. Let's Google it. Hang on. Yeah. Oh, a control group. That makes sense. Yeah. Oh, I just always call them C groups. Okay, cool. So, what else about process isolation? Okay, so so these C groups can do a lot of things. They can restrict a lot of things. They can set permissions on in a lot of different ways. So if we give our app, for example, like 1 gig of RAM to use, and we define that, and that's like a strict parameter, if that app starts to use more than that, it's gonna get an out of memory error and it's gonna get killed. So C groups are gonna be like the mechanism that helps to isolate that. So yeah. Okay, so interacting with Linux. From a CLI perspective, you can either do that manually, right? So you open a terminal, or on Mac would be your command prompt, and you're going to sit there and physically write some commands. You're going to tell it to make a new directory or make a new file, whatever it is. So that's one option, and then your second option is scripting. So you're going to write a little script, and then you're going to run that script. Those are the two things that we're doing with Linux. That's how we interact with Linux. none, like when we're using cloud computing, we're not really using like GUIs. We don't really have, other than the terminal. The terminal is our GUI, but we're not going to have, you know, like when you're running Linux on like a desktop, like a personal laptop, and you have like your applications available to you and like your file system is there and it's laid out. That's not how we're interacting with Linux when we're doing cloud computing. We're really going to be doing a lot of terminal typing, scripting, things like that. So getting used to running Linux commands is important, and you'll totally get there. So if you've never, yes, did you have a? Yeah, exactly. Yeah. So with WSL, that's the WSL's Windows subsystem for Linux. Yeah, you install that, and actually, it's part of assignment 1 for Windows users. You're gonna have to install WSL. It's pretty fast and straightforward to do. But yeah, and then you can open a terminal. You can use like the Unix commands that you would use on a Linux box or on a Mac box. Yeah. So is that clear? There's no like a web browser that we're gonna pop open. If we want to interact with something that would run as a web browser, we're gonna do some port forwarding so you can access it from another machine. But when you're on your Linux box, it's just the terminal. It's just your shell. Sound good? All right. Oh, terminals and shells. Okay, that was the next one. The terminal is the program that provides you that user interface. That's your only user interface. And then the shell is the program that runs inside the terminal. Just to, I don't know, we use them kind of interchangeably, the terms, but like the terminal is the program, the shell is the program that runs inside the terminal. Yeah, the shell is going to offer like, you know, input and output handling. It supports variables, all those things. Okay, so there's so many different kinds of Linux, and it can get a little overwhelming. There's because it has a long history and it's open source, and everyone's like, wait, I have a good idea. I want to make Linux do this thing, and it's kind of wonderful. And everyone, you know, ends up with some strong opinions about, like, eventually they end up with some strong opinions about, you know, which distro is the best and which one is going to be the best for my job and things like that. And that's cool and good for you. Like, have strong opinions. I think that's awesome. But they kind of fall into these key categories. So we have these distro families, and those are going to be Debian, the Red Hat Enterprise Linux, SUSE, and other distributions. We're only really going to look at Debian and Red Hat Enterprise Linux, but even then, not so much. I don't really use Red Hat that much, but if you like it, if you already know you like it, that's cool. You know, given it's like, so Red Hat Enterprise Linux has enterprise in the name, right? Like, it was built for enterprise. You know, it has licensing that's not quite the same as the rest of the Linux world. And because of that, it's kind of its own little bit. Fedora is a little different because it actually then is free and open to use. CentOS, Oracle Linux, those are derivatives of that. So these are just kind of like, you can think of them as like forks of each other, right? So it's like you start off upstream, but the nice thing is that, like, when a push gets made to Debian, that will make it into the Ubuntu ecosystem, and that'll make it into the Mint ecosystem. So those are upstream and downstream distros, right? So yeah, Ubuntu is really, really, really common, really popular, very popular choice for servers. There's other ones too, and clouds are starting to have their own Linux distros. So like Amazon Linux is now become really popular, and Amazon created their own Linux distro to optimize their Amazon like resources that you can virtualize. So that's cool, good for them. You can't use Amazon Linux outside of Amazon, really. So is that open source software? I don't know. It's free to use, right? Anyway, there's some complications. It stops being so cut and dry pretty quickly. Open source world is interesting. Yeah. So, oh yeah, and Arch Linux is the one that is like the most customizable, and, you know, it gives you like bare bones. You get like nothing with it, and then you get to really just like hack into it. So yeah, we all have that Arch Linux friend. Okay, but like, here's a larger landscape of this. We're just talking about a couple of families. There is so much out there, you know, going all the way back to the 90s. And like, you can kind of follow the streams, like the Debian fork is kind of up there. You can see how it kind of, and it sort of explodes, right? In the late, I guess like 2010, what is it? The aughts? I don't know what to call it. yeah, so it starts to explode over there, and it kind of keeps growing from there. And you can kind of drill down even on one of those and just keep following the paths. And it's cool. And some people get really, really, really hyper specific. But yeah, so we're bringing all of this up because a lot of these options, in addition to the computer architecture that you want to run when you're spinning up a VM in the cloud, a lot of different Linux distros and operating systems are going to be available for you. So, you know, how do you choose? How do you start to choose a Linux distro? Well, there's going to be like some optimizations, and it's a good thing to kind of look up, like, you know, there's going to be some things that play better together, or maybe you like a particular package manager. You know, maybe you need Red Hat for something, like, you know, maybe there's some really custom software from back in the day that was only built for Red Hat Enterprise Linux, because it's enterprise world and someone made a lot of money doing that or whatever. So you kind of choose if you need like Debian or Red Hat branches. Are you going to develop primarily for the cloud or for the desktop, or are you developing primarily for a container? There's different optimizations there. Do you need like the newest available or the most stable package? You know, there's considerations there too. Primarily in this class, we're going to be using Ubuntu, like across the board, pretty much. If you have really strong opinions about using something else, you're welcome to. That's fine. But you know, I really like the apt package management ecosystem. Ubuntu's really stable. It has like longevity. There's like long-term support. So you could kind of reuse these assignments if you wanted to, you know, go actually spin up a cloud resource after the class ends. You could have that running for the next 5 years or whatever it is. It's just friendly. I think it's super friendly. And there's always instructions for, like, there's always going to be instructions like how to do this on Ubuntu, because it's really, really common. So if you get stuck, it's an easy one to get yourself unstuck with. Okay, we have a tiny bit of time. And so I want to talk about open source software more generally, more broadly. So we had a quick definition of open source software. It's just going to be software that's released under a license, and that license is what makes it open source. It's really just, it's a license file, you add it to your repo, and that's it. And there's a bunch of different kinds of open source licenses. Some let you, some will have strict criteria that you cannot monetize it in any derivative software. Some don't have that. There's a bunch of different options out there. But basically the software, if it's open source, you're going to be able to access it, you're going to be able to modify it, and you're going to be able to distribute it how you want to. It also allows for open collaboration. There's some licenses that require you, as you make improvements, to share that back with the community as you make those improvements. I don't know how anyone would enforce that, but you know, that's kind of the expectation. And open source contributors like take this really seriously. It's part of what it's, you know, I mean, yeah, if you are running on a Unix kernel like I am, you know, that's open source software. It just like it powers the whole world, and it's worth it to give back. So yeah, open collaboration, and in general, open source software is free to use. There's kind of two schools of thought on that. So there's the open source initiative, which is the OSI, and they don't make a distinction between like the free to use and just like open to use. There's the Free Software Foundation, the FSF, and they consider free software to be a subset of open source software. So they think there could be open source software that you can monetize, and that's where you get these like AGPL licenses, things like that. Whatever. It gets kind of hairy, but another key differentiator, or a key thing about open source software, is that the source code is available, right? So it's like, it's not just like a program that's free for you to download or whatever. I mean, that is part of it, but the source code has to be available, you know, and available. It's not like, oh, let me like decompile this and like reverse engineer it, and now I have my source code available, right? It's like actually that the source code is there for you to adapt, modify, contribute to. So can anyone think, we only have 5 minutes, but given you know, what we've talked about so far about like Linux, we've talked about these different instruction sets, we've talked about you know, a little bit about open source. Why would, and like vendor lock-in, like why do you think open source software and cloud computing are like so important to one another? Really, open source is important to cloud. I think open source could take or leave cloud. They don't really need us. But yeah, but why would yes?
would have.
I'm sorry, so what was the first thing that you said?
The pro would be cost efficient.
Oh, yeah, cost efficiency for both. Yeah, absolutely, right? Because if we offer an open source, but when I say we, I mean the cloud world, like, since I work for a cloud, but like, when we offer you an Ubuntu image, for example, to use, we're not paying Microsoft a license, right? Like, we don't have to explicitly pay another vendor in order to have that available for you. So it saves us money for sure. And then it saves the end user money, because if we did have to pay for that license, guess who's actually paying for that, right? It's not really us, it'd be you, right? And you can spin up Windows machines in like Azure and obviously imagine if like Azure didn't let you spin up a Windows machine. But yeah, but then that price of that license gets passed off to you. What's another pro of using open source with cloud?
I think it makes it less. Whoever's developing the software, like if they stop, like if you're, buying some software from some organization. And that organization wants to increase how much they're charging you, or they stop developing it or whatever. You don't have access to the source code, then you're like.
Yeah.
Spend a lot of money finding something else. So.
Totally. So you are kind of reducing your supply chain risk, right? Your software supply chain risk by using open source. So yeah, it's a really interesting take. Yeah, that could absolutely be a reason. When open source projects end, there's like a long tail fade out. But like as maintainers kind of quit, then there's like a big push in the community to kind of get people more up and running. Yeah, great point. Yeah.
Kind of with that modified distribute, similar to what you were saying, there's a lot of like software and cloud environments built on specific versions of software, specifically the open source software. And as new versions come out, people have the wrong version, it can break stuff. So having those old versions available through the open source world, things like GitHub and there's some package managers that do that. Really allows people to continue using this piece of code that maybe was built years ago and only runs on Python like 7.
Yeah, totally. So is the key like connection with cloud computing is that like there's more longevity for the consumers so that they can keep their.
Say is it Docker has the ability to downgrade for like specific package versions if needed.
Yeah, it's not just Docker. Yeah, you can downgrade packages using like Poetry if you're using, yeah, totally. A lot of package managers will let you. Yeah, totally. So what it's doing is and correct me if I'm not really articulating your point well. What it's doing is it's providing a degree of protection against breaking changes. Yeah. Cool. Yeah, absolutely. Why else? Why else might we want open source in cloud world? Do y'all know how much clouds like what the size of that market is? Yeah, the hyperscalers make an insane amount of money, right? And a lot of the money that they make is not really from necessarily like the core building blocks of cloud. A lot of it is from really specific solutions that they offer you and that you end up paying a lot of money into. If you start to develop your program, your application, like using that with that in mind, right, with these particular platforms in mind, if you're not building it on an open source like foundation, then you have extreme vendor lock-in, right? And it's kind of like the worst of all worlds. So yeah, choosing open source solutions helps you move around to different clouds, right? So if someone's stability like is really, really poor, or if someone's like uptimes are just not what your SLA needs, you can take your application and move it to another cloud because you're running it on open source. So because clouds know that, we have an incentive to maintain or to contribute to the open source community as well, right? So the Cloud Native Computing Foundation is a subsidiary of the Linux Foundation. So Linux Foundation was created to support all the Linux maintainers and all that stuff. Cloud Native Computing Foundation is a subsidiary of that. The OpenSSF The Open Source Software Foundation works with like the CNCF. This is a big like collaborative ecosystem to make sure that we have checks and balances in place and that like clouds are, because like, yeah, I mean, the amount of power that the big clouds have is absolutely insane. And so making sure that there's checks and balances to prevent just like runaway, like, you know, profit off of the applications that you want to run is pretty important. So it kind of keeps your cloud costs down also, not just because you're not able to leave, but also because you're able to kind of customize your stuff. You're able to run your services with open source as like an option, right? You don't have to use SageMaker. You can learn how to do it with open source and you're not tied into SageMaker. Not to pick on AWS. I have friends at SageMaker. They're lovely. But yeah, so that's another benefit. Kubernetes is an open source software project. I was the first CNCF graduated project, and Kubernetes now literally powers the entire internet. If Kubernetes were not open source, like the cost of everything would skyrocket. Yeah, there are cons. I'm so sorry, we're over. There are definitely cons to open source, and we'll talk about those at another time. But yeah, this is thanks so much, everyone. I'm
Thank you.
glad you're here with us. Thank you.